So this is the second problem set for Chapter 6. And the first problem I want to look at is I want to look at a turbine. So in a turbine, and by turbine, we're considering this whole system. Usually we refer to a turbine. But in this problem, let's just look at this section that's the actual turbine. Turbine is actually, in practice, it's referred to as the compressor, combustor, and turbine section, but we're going to just look at the turbine. So we have these very high, hot gases coming out, and maybe this is actually an example of a turbine, now that I'm looking at it, of a gas turbine, but we may be talking about a steam turbine. In either case, you get the point. We have a very hot steam or gas mixture coming into our turbine. So we have steam at 10 megapascals and 500 degrees Celsius coming in. And coming out, we have 10 kilopascals, and we have a quality of steam of 90%. So we know it's a saturated liquid, saturated vapor mixture, mostly vapor coming out at the exit. Okay. And here's kind of a little reminder of how we use quality. So we're going to use this average term. So here I've written it in terms of specific volume, but we can easily replace specific volume with enthalpy. So I'll just write enthalpy in place. And we can do that with any property here, as long as we know the quantity. So what we're trying to find is the mass flow rate, so that for these conditions we can extract a power output. So this turbine would provide a power output of 5 megawatts. So let's see, this would be 5 megawatts, or 5 million watts. Okay. So what do we do? Well, I'm going to start with just writing down what is it that we know. So what do we know? Okay, what do we know? Well, at point 1, we know that the pressure is 10 megapascals and the temperature is 500 degrees Celsius. If we look on our tables, we can show that, and I'll let you guys do that this time. I won't refer to the tables in this lecture, or maybe I will. Maybe I can help you guys with that a little bit. So let's see. So for this particular mixture, if we look at our property tables, and let's say 10 megapascals and 500 degrees Celsius. So let's go to the pressure tables. 10 megapascal is 10,000 kilopascals. So anything above 311 degrees Celsius would be a superheated vapor. And what do we have? We have 500 degrees Celsius. So we have a superheated steam for this case. Okay, so we have a superheated steam mixture, or a superheated steam. So let's go to 10 megapascals. And then we need to look at 500 degrees Celsius. So we go here to this column right here. And we can write down our values. Let's go ahead and write down our enthalpy. So 3375.1 kilojoules per kilogram. So our enthalpy here is going to be, let's see here, 33. So enthalpy in is, let's see, 3375.1 kilojoules per kilogram. How about at point 2? And by point 2 I mean the exit. And I just wrote that value down for 500 degrees C right here. Okay. So for point 2, we know, since it gives us a quality, we don't even have to check really what the state is, because since it's a quality, we know it's a mixture of a saturated liquid and a saturated vapor, some type of mixture. The quality is 90%. So we know it's 10 kilopascals, and since we know it's on that saturated line, let's go up to our tables. So for 10 kilopascals, we know that it's exiting at 45 degrees Celsius here. And what we'll write down is we'll go ahead and write down the values for sorry for that. So we'll write down the values for the enthalpy. So we'll write down HF. HF is, in this case, 191.81. And the reason I'm writing all of these down is because we have a quality mixture. So we need the HF value, which is the saturated liquid value, and I'm also going to write down the HFG value. So that is just the subtraction of Hg minus Hf, and it just helps simplify it a little. We'll write one last step here. So HFG is 2392.1 kilojoules per kilogram. And so now we have enough information on how to evaluate. So we're going to find an H average using our formula that we have. So our H average is the HF, which is 191.81 plus 90% times HFG. So this is 2392.1. So if we do this calculation here, we would get, let's see, 23,447. Let's see, I think that's correct. 23,447.00 joules per kilogram. Okay, so now that we have that information, let's see if we need more. So I haven't worked this problem out completely yet, and let's see if we need more information. So in the next step I'm going to do, and remember we have a toolbox. So far we've talked about the conservation of energy, and we've also talked about the conservation of mass. And we don't really need the conservation of mass here, as far as I can tell, because that's what we're trying to solve for, right? We just know that there's, let me move this out of the way. We just know that there's a mass coming in, and there's a mass that is leaving the system, and it should be the same amount because mass is conserved. So next thing I'd like to do is let's just go ahead. The only other thing that we have is the first law of thermodynamics, so let's just write it down. Q minus W. Mass, since mass is the same at the inlet and the exit, I'm going to write it here, mass flow rate. And we have a change in enthalpy, since it's an open system, plus the change in kinetic energy, plus a change in potential energy. And we've already stated that kinetic energy and potential energies are the same. We're assuming that it's adiabatic. We're not losing any heat. And it's a valid assumption because these turbine portions of these power generations units are usually pretty well insulated, so we don't lose this heat. We want it to be really hot. So we have minus W. Now, the W is coming out of our system, so we're getting work out, which is positive. And since there's a negative sign already here, so here's the negative sign, I'm going to leave it as negative. So this will be minus 5 million watts. Mass flow rate, we don't know. And the delta H is going to be, or lowercase, I'm sorry. These all should be lowercase. Delta H, or let me expand this. So this should be H2 minus H1. Well, I'm going to absorb that negative sign into this bracket here. I'll just rewrite it as H1 minus H2. So I just flopped the negative sign, absorbed it into that bracket there. Now what we can do is we can solve for the mass flow rate. So this would be 5 million divided by H1 minus H2. So H1 in this case being the value of the enthalpy at the inlet, which is 3.375 minus 2.34700 joules per kilogram. So I converted those values to joules that we talked about earlier. So solving for this, we get 4.852 kilograms per second. So that's the value that we need in order to meet all of the requirements set by the first law of thermodynamics. Okay, so that, I think that's a good example for you guys. It's practical as far as something that is used in a power generation system, and it's a calculation that you can do to make sure that you don't violate the first law of thermodynamics. All right, last problem from chapter 6, again dealing with an open system. Let's talk about a hairdryer. All right, so a hairdryer we have is basically a fan. Okay, we have a fan here. It's moving air through our pipe or our tube, and we pass the air over this resistive heating element. The air comes in at 100 kilopascals, so just atmospheric pressure air. Leaves, let's say it leaves also at 100 kilopascals. Now the point where we take the velocity in, we'll just say it's so big over here that the velocity is 0 at the inlet. And by the time it exits over here, well, that's a terrible line I'm drawing there. Let's see if I can improve that. Oh, that's somewhat better. Anyhow, the velocity at the exit there would be 21 meters per second. And it would be heated from this resistive heating element. It's providing 1500 watts to 80 degrees Celsius. All right, so we want to find out here the mass flow rate of air needed to make this happen, and also what's the volumetric flow rate at the inlet. Now keep in mind that the density is changing here, right? Because as we increase the temperature of air, the density is going to change of air pretty significantly. Okay, so we can't neglect that density change. And of course we have the constraint here, use the CP of air at 300 K. So let's get that first. That's probably the easiest thing. Okay, let's go to their table. Now I hope you guys can see this. I have no clue, so I hope that you guys are able to see it. I don't know till after I make the video, so apologize for that if you can't. Anyways, I'm on table A2, but let's go to A2, letter B, where we're looking at air, and we're going to get the CP since we're dealing with an open system. So CP of air at 300 Kelvin is 1005 joules per kilogram, degrees Kelvin. Okay. All right. So let's proceed here with what we need to find. So in our toolbox, we have conservation of mass. Now, what's coming in is coming out. We know that. That's equal. Since we don't have any other inputs, we're assuming it's a steady flow system. So we're assuming it's a steady flow. Nothing is changing with time. Well, the only other tool we have is First Law of Thermodynamics. So let's write that. So Q minus W. Mass flow rate's the same for the inlet and the exit. So we'll say this is delta H plus delta kinetic energy plus delta potential energy. Okay. Now, what terms can we neglect here? Well, we'll assume that this duct here is adiabatic, that there's no heat losses through this duct, that all the heat that's going from this wire gets transferred to the air that's passing over it. So we'll assume that there's no heat transfer. Now, keep in mind, there's heat transfer from the coil to the air, but that's within our system, right? We're talking about, when we talk about Q, this Q is outside of the system. Is there something going out of the system or into the system that's heat? Okay, and really what we're providing here, and I've written it as 1500 watts, but what's coming in through here I'm considering as work, since we're thinking about it in terms of voltage and current. So we're putting work into the system. When we put work into the system, this is a negative value when we go in. So a negative times a negative is a positive. So we're going to have a positive 1500 watts. And this is equal to the mass flow rate times the change in H. So we'll say this is H2 minus H1 plus the change in kinetic energy. Well, let's not neglect, since we don't know what the velocity is, or we do know the velocity at the exit. It's coming out at 21 meters per second. I'm going to not neglect it, okay? You may be able to, though, neglect it, but let's go ahead and use it, okay, just to be more accurate. So let's go ahead and say this is V2 squared. And just to comment on that, you know, a lot of times the potential and kinetic energies, and here of course we don't have any potential energy change, it's all on the same plane, the airflow rate. There's no elevation or decrease in elevation on the plane. So knowing that, what I was saying is that the kinetic energy values and potential energy values a lot of times are just so small compared to the total energy, the enthalpy, and the internal energies, that we tend to neglect them. And this is a good illustration here that I'll show you. So so V1, remember V1 is 0. This is 0 here. V2 is 21, so it's coming out pretty fast. So despite it coming out pretty fast, we just we maybe could neglect it, and we'll just see how much of a percentage it is of the total value. But we don't, right now we don't know what H2 minus H1 is. Now, there's a couple things you can do. We can look in the back of the text, okay, and get some values for the enthalpy of air at this temperature, or we could just use an average value here. This CP we can use to calculate. Remember, delta H is equal to CP delta T. Right? Remember that from our lectures here? So CP is 1005. And remember, this is H2 minus H1 times T2 minus T1. So this is 1005. And then T2, temperature at the exit, is going to be 80. I mean, we can express it in terms of Celsius or Kelvin as long as we're consistent. I'll just use Celsius, I guess. 80 minus the inlet temperature, so 273 minus 300 is 27. So this comes out to be 53265 joules per kilogram K. Oh, I'm sorry. Joules per kilogram. All right. I must be getting tired here. I can only imagine how you feel watching these videos if I am getting tired. So we'll go ahead and do 1500 equals 2. Let's go ahead and plug this delta H value into our equation. So this is 53265 plus, and now let's go ahead and solve what this is. So this is 21 squared divided by 2 plus 220.5 joules. So you see the kinetic energy is a very small portion. So the enthalpy value is 53,000. The kinetic energy is 200. So it's 2 orders of magnitude difference. So even if we neglected it, I mean, I don't know how much more of a difference it would make in our final answer, but I chose to include it here just as an illustrative purposes. Anyways, we can go ahead and solve for our mass flow rate. Our mass flow rate here would be 0.028 kilograms per second. Okay. And now we can find, let's also find the exit volumetric flow rate for the dryer. And the exit volumetric flow rate, remember, we have this, we know that the mass flow rate in is equal to the mass flow rate out. Because we don't have any other inlets, we don't have any other exits, okay? So we just solved that this number comes out to be 0.028 kilograms per second. Okay. So if we expand mass flow rate at the exit, this is density at the exit, area at the exit, velocity at the exit, 0.028 kilograms per second. Density at the exit, we don't know, and we can combine these two to be volumetric flow rate at the exit. So let's go ahead and find density. Now, is there any other property or any other equation that we have to find density? Is there anything else that we can use to find density? Well, we can find density using the ideal gas relationship. P is equal to rho RT. And these are, of course, all at the exit. So the pressure at the exit, we already talked about, is 100,000 kilopascals. Density at the exit, we don't know. R value for air, we can calculate it, or we can just go to our table here and look it up, right? So here, gas constant for air is 287 joules per kilogram Kelvin. So I'll write that here. And our exit temperature is given at 80 plus 273. And it is important to write absolute units for this equation. So the density at the air at the exit is 0.9871 kilograms per meter cubed. All right, so we get this value, plug it in here, which is right here. Our velocity flow rate at the exit comes out to be 0.0284 meters cubed per second. Okay, so that's your final answer. All right, guys, I went a little bit long on this lecture, but I hope these examples helped you, will help you to study a little bit and find some applications of this in practice as well. So we'll start talking about Chapter 7 in our next lecture.